Let's see another question, homework question in chapter 3. Actually, we give the answer of this question and explain very carefully on class. So I don't think we have to do it again. It takes a long time. And in here, just a very quick review of the question. So it said, after the construction of a concrete retaining wall, this is a retaining wall, backfill material from nearby borrow pit, this is a borrow pit, was brought into the excavation behind of the wall. We bring soil from this part, from here, to fill up, to compact it and fill the back of the retaining wall. And it is said that in here, the void ratio is, we want to reach is 0.8. And from the pit, because soil is accumulated, it is nature soil, the void ratio is high, 1.1. Ask you to determine the volume of borrow material. You need to construct 1 cubic meter of compacted backfill. Actually, if you know 1 cubic meter compacted backfill, how much soil you need to bring here to compact 1 cubic meter. If you know the volume in here, then you can calculate how much soil you need to borrow from this place to here, right? And then arrange the machine to transport soil from this place to this place. It is a very practical problem. And the clue to solve this problem actually is this. You need to find an equation between these two, between the borrow pit, the soil from borrow pit, and the compacted backfill. What's the equation in here? The same thing in here. The same thing first you need to keep in mind. The soil mass from here to here never changed, right? The only thing we changed in here is just the volume. The volume changed is just because the void ratio changed. We compacted very loose soil in here, to the dense to here, because we compacted the void ratio, right? So the void ratio from here to here reduced to 0.8. This is an important thing, right? So actually you need to got an equation, the equation that is mass is the same. The mass is the same, water content is the same, solid part is the same. Different thing is just a void ratio. So if the mass is the same, that is the solids is the same, then we can go to this, right? This is the dry density in that side, dry density in this side, and the volume in that side, volume in this side, right? So we say that if we want to compact the soil into 1 cubic meter in here, so the volume for VC, for the volume in here is 1 cubic meter. Then this is 1. So the density in here should be equals to the dry density of this. Should be equals to this, right? So then VB, how much of VB? VB actually equals to the density from this side divided this side. Got this. And the density, the ratio of density equals to the ratio of unit weight. And because unit weight can be calculated with this equation, we know void ratio, then we can got the results, right? This is a clue. You need to find what is the balancing between the borrow pit and the compacted backfill. The balance is actually, the same thing is actually the mass of the soil. Or we say the solid of the soil. Because moisture is the same. Nothing changed. It's just a void volume, right? So we explain this answer on class. For this question, it is easy. It's just to use equation, but you need to choose the right equation. In here, for example, it asks you to choose the relative density, because relative density you can use this equation, this equation, this equation, this equation. You can always find an equation on our textbook to calculate the answer. But which equation you need to use? You need to go carefully. What is the known parameter? In here, it gives you what? It gives you the maximum and minimum dry unit weight. So dry unit weight is what you need to use, right? All of this equation, only this use the dry unit weight. So you need to choose this equation, not this, not this. Some of us students use those unit weight, try to obtain N and obtain E or obtain rho, and then do the calculation of dr. Make things complex. You directly use this equation. That's all. And then let's see a homework in chapter 4. In chapter 4, it says we learn plasticity, right? So how to determine the liquid limit and plastic limit is important. So in here it said the following data were obtained by conducting liquid limit and plastic limit test on soil collected from the site. Apparently it gives you numbers of blows. What method it used? Numbers of blows. Percussion cup method, right? So we use percussion cup method. Ask you to draw the flow curve and determine the liquid limit. You've got the number of flow moisture content. Draw the flow curve. The x-axis is numbers of flow, y-axis is water content. You got the two numbers in here, two columns of numbers in here, just draw the plot. But the x-axis is in a log scale, keep in mind, right, in here. And then ask you determine the liquid limit. So how to use the flow curve determines the liquid limit? We say that the liquid limit actually is the numbers of flow of 25, the corresponding water content for the numbers of flow of 25. So you need to find 25. This is 10, 20, 25 is around here. And draw a vertical line cross to the flow curve. And then draw a horizontal line. And in here it is around 36 point, maybe, let's say 7. So this is the definition for liquid limit test. For percussion cup, you need to find the water content corresponding to 25 blows. Okay? And the x-axis must be in log scale. So then you find the liquid limit, right in here. It is 36.7%. And it tells you plastic limit is 19.3%. This is plastic limit. And you use and then you can calculate plastic index. That is the difference between liquid limit and plastic limit. That is 17.4, right? This is plastic index. So why we calculate plastic index? Because the second question he asks you, using the Casagrande plasticity chart, asks you determine the soil type. So if you want to use the chart, let's see, this is the chart. The chart is the relationship between plasticity index and liquid limit, right? So we know liquid limit, but you need to know the plastic index. This is why we calculate plastic index in here. So we got plastic index liquid limit, and we can locate the soil on this chart, right? So liquid limit is around 36.7. 30 is around here, 36.7 is around here. And the plastic index is 17.4. This is 17.4 is maybe around here. And this is 36.7. So the soil should be located in here. Let's see. For the soil, this is inorganic clay. This is the first one, second one, third one. Third one is inorganic clay of medium plasticity. So this is the soil type we determined, right? So this is the answer for this question. Very easy. So the flow curve, you need to know how to plot a flow curve from a percussion cup or a four-core method, right? And then how to use the curve to determine liquid limit, and then what's the definition of plastic index? That is the difference between liquid limit and plastic limit, right? So this is the answer of this question. Let's say Chapter 5. Chapter 5 is about soil classification. The soil classification question in soil classification need a very big chart, so we didn't actually have any examination questions in chapter 5 because we don't want to attach too much tables, and it actually tells you a lot time to answer the question. But actually, this kind of question is not difficult. You just need to find one by one. That's it. So we don't go go into this question. The answer for this question. Okay. So yeah, you see, we just need to allot big charts. If you are interested in, I will attach the PowerPoint to our group, so you can try to work on it yourself. Let's see one question in chapter 6. It says for a soil with GS 2.7, ask you calculate and plot the variation of dry density with water content 8, 12, 16, and 20, and for the degree of saturation at S equals to 45, 70, 85, and 100 respectively. So you need to calculate the dry density at the water content of 8, 12, 16, and 20 under saturation degree of 55, and then the same thing under saturation degree of 70. The same thing, that is for water content under saturation degree of 85, and for same water content under saturation degree of 100%, right? So what's the equation we need to use? We need to calculate dry density, right? For dry density in here, you see, this is a dry density equation. Which one we should use? You want to calculate dry density with no water content, and we know saturation degree. No water content, you can use this, but you have no idea with moisture water content, right? So with the moisture unit weight, so we can't use this one. And in here, yes, we know GS. You don't know void ratio, so you can't. It's difficult to use this. But for here, we know water content, we know degree of saturation. We have no idea of porosity N. So for this two, actually, we can try to find void ratio, right? With this equation, we can try to find the void ratio. Can we do that? So let's see what is void ratio. In here. So void ratio equals to this. We can use this to calculate void ratio, right? So water content we know, GS we know, SR we know. We can calculate every single void ratio corresponding to different water content and saturation degree. And then put this void ratio in here, then we can actually calculate the different water content, different saturation degree, dry density, and different water content and saturation degree, right? So actually, the equation we need to use is this. The relationship we need to use is this first, and then this. Let's see the answer. So, if we know that water content is this, right? And we know degree of saturation is this 4. So what is the void ratio? So the void ratio for water content of this 4 under saturation degree 0.4055 is 1, 2, 3, 4. We can use this to calculate it, right? Because water content you know, saturation degree you know, and GS you know it is 2.7. Then you can calculate void ratio. With the same one under another saturation degree for those 4 water content, then you can calculate void ratio for those 4 water content. For the third saturation degree for this 4 water content, then you can calculate 4 different void ratio. And again, 4 different void ratio under saturation degree of 1. So you calculate actually 1, 2, 3, 4, 5, 6, 7, 8. We calculate 16 void ratio because we have 4 water content under 4 different saturation degree, right? So 4 times 4, that is 16, right? So we have 16 void ratio. Put this 16 void ratio into here, then you got 16 dry density. This 16 dry density for the water content of this 4 under 4 different saturation degree, right? So we got the dry density 16, and then finally you can plot it on the dry density and water content plot. Then we got this. This is 4 degree of saturation 0.55, 0.75, 0.85, and 1.00, right? So this is the answer. Let's have a break.